Jesús said in his presentation, namely concerning the downscap. And actually, you ask this question about what happens if one wants to apply this technique to this space. And it is known, I should have said, that it is known that this space is contractible, but it is not collapsible. This cannot be done in a naive way. But still, the original question was if the downscap, which is dimension 2, can be reduced perhaps with a suitable vector field, the gradient field, to something of dimension 1. And I'm very curious to see that. So I'm going to switch a little bit, going into the description of this algorithm that I want to present to you for computing discrete gradient fields in any general simplicial complex. And there are several also variations of this stuff. So let me start just a little bit first, formalizing a little bit some of the ideas. So let's start with X CW complex. And suppose this is regular. Regular means that the attaching maps are really nice. Each cell is going to be attached to the previous skeleton in a way that it is a homeomorphism in the boundary. So it doesn't go back and do some strange things. All right, so I just want to just make a little bit more formal the stuff that I was presenting in the previous talk. Once we formalize this a little bit, then I'll give you the algorithm. Now, the next thing is a little bit of notation. So suppose you have a couple of phases, alpha and beta of X. I'm going to be, if I want to make explicit their dimensions, I'm going to write it like that. Alpha is supposed to be a phase of dimension P. Beta is supposed to be a phase of dimension P plus 1, which means that essentially if this is thought as an abstract simplicial complex, this has P plus 1 vertices, and this has 1 additional vertex. And then I'm going to use this notation to indicate that this is a phase. It would be a phase of codimension 1, which means that out of these P plus 2 vertices, you remove 1, and this would be what you get at the end. Now, one special character in this whole thing is the phase poset of this complex. And this is essentially the set of phases. Similar, like if it's, well, it's essentially the simplicial complex. Or well, or the regular complex. See, the bad thing of using your phone is that you receive calls. All right, and this is, I'm going to thought of this as a poset. Namely, there is a relation between phases when one is contained in the other. And this is alpha is less than beta, as you can see it here, if alpha is a phase of it. Or if you think of the closed sets, if alpha is contained in beta, and this is a well-behaved relation because essentially your complex is regular. Now, a very nice thing to do here is to play around with the Hasse diagram. Of X. But Hasse diagram is nothing but what I already said. You think of the phases, the set of phases, together with this relation, but you sort of write them in an order way. So here you're going to have the top dimensional cells, and on the bottom you start putting cells of dimension 0, cells of dimension 1, namely here you put vertices, edges, triangles, and so on, if it is a simplicial. If not, you can do the same thing. Let me just think that this is simplicial for the moment. Simplicial complex just works the same. And then, well, you make your list of phases, whatever, and then you have, I'm going to think of this, the Hasse diagram is essentially this, with this order, but I'm going to make a conventional agreement that I'm going to think of it as a directed graph. Namely, well, there's going to be vertices are the faces, and there's going to be an edge from one face to a previous one if this guy is a face of that, in this sense. And then you have these kind of things. And just by convention, I think of this, of all of them as pointing downwards. For instance, what would be the Hasse diagram of the solid triangle? Solid triangle has 3 vertices, 3 edges, and something in dimension 2. So one has 3 things, 3 vertices, 3 edges, and then 1 single thing. And for instance, if you think of the Hasse diagram, it would look like this. Namely, let's make the diagram. This would be A, B, C. So this is A, B, C. This is X, Y, Z. So X goes from A to C. So let's replace this. So this would be X, which has A as a face as well as X. This is represented in here. And then from C to B, one has Y. And from B to A, one has Z. If I didn't think it incorrectly, you will get this picture. And then the 3 faces of omega would be these 3 guys. So this is a standard representation of the combinatorial structure on a simplicial complex like this. All right, now, let me just use this. The only thing that I want this projection is because of that. No, wait. So what's so important about a height function defined on a simplicial complex so that I can make work this idea that I was talking about in the previous session? Well, the idea is to put heights on the cells in such a way that one has a well-defined notion of deforming things. But that's still very geometric. This is topological. It's deformation. So, but I want to discretize it. I want to be able to tell the computer, look, you're going to be making this movement, but in a discrete way. So what you have to do then is, well, stare at this picture. What's so special between the first image and the second image? Well, it's special in the sense that first image is kind of the stock. It cannot be deformed. It can be stretched, but still keeps the same figure. However, in the other one, you can just deform thing and the whole thing goes to a point. Well, let's see what happens. Notice that in the top case, the 2 cell, which is right on top, has the 3 faces in lower dimensions, like in there. So if you go from a 2-dimensional thing to its faces, which are of dimension 1, function decreases. And the similar thing happens for, say, the first edge. The edge that would be the one that goes from 5 to 8, there. And its barycenter, namely that cell, it's at height 9, and its 2 faces, which are 2 vertices, are lower. One in height 5 and the other in height 8. So every time that you go from one face to one of its faces in one lower dimension, in the situation above, you decrease, and you decrease. So that's kind of boring. That will be critical. But however, in the other situation, this does not happen. So what's so special? For instance, look at the blue point that is more or less at the level of 9, height 9. So it is the barycenter of the top cell in the blue triangle, right? So if you go to its faces, it goes down. It's similar to what happens to there. Lower faces would be lower. Lower dimensional faces would be in lower height. But look at the body center of the body of the body center of the two-dimensional cell. If I go to the sides, to the edges, I indeed go in lower height. But there is one direction, if I go to the other, in which it goes up. And this is actually its only exception for not having this rule that if you have a cell of dimension d and move to one of its faces of dimension d minus 1, but if it goes up, then this is a good thing because it would look like that and it will tell you that you have a particular gradient line that wants to go down from the top edge to this. The special definition is the following. Of a so it will be a function from the phase function of it as the family diagram of x into, say, the real numbers. It might be just the integers because I'm going to be finite. So there is a finite number of phases, and then it will take a finite number of points and whatever. It doesn't really matter that this is the real. Could be just the integers, positive integers if you want. And so essentially what is an element here is a cell. It's a phase. It's some simplex and making up this whole complex. And I'm going to be assigning to this phase, to each one of these phases, a number. Think of that you're assigning an height to the barycenter of the corresponding cell. Well, this is going to be Morse function if the following happens. Look, well, fix a phase. Then the following, for any such phase, the following must happen. Look at the set of phases. So suppose this is of dimension p, and look at the set of b's, so that b is a phase of alpha. But even though it is lower dimensional, and notice that it is a 4-dimension 1 phase. But even though it is a smaller dimensional phase, its value is no less than the value of the higher dimensional phase. Well, I want that this is kind of a problem, like the one that I was describing there. I want that there is a limited number of such problems. Every phase, except for one of its lower dimensional phases, it always goes down, but perhaps with one single exception. And this should be happening. This said, there is at most one exception. It could be no exception, for instance, like the one on top. And also, if I consider, but now co-phases, phases above, co-phases. So that alpha is a phase of gamma. Again, it's only codimension 1, and I'm looking at all the co-phases of alpha, but in such a way that there is a problem. And again, one wants that there is at most one such problem. This is all that there is. So this is capturing these kind of things. There should be a very definite way of saying if there is going to be a movement, it's only one. Otherwise, you would lose. You would have to tear apart this space for making a hole and then making two different moves. Because these kind of exceptions are going to be then encoded in something that we're going to define as a gradient field. All right, so we can just remove this. How do you flip this. And then the eraser. Do we have an eraser? Ah. Ah.
Sorry. So this for each fixed alpha, right?
Yeah.
And so the analog in the usual case is that for each critical point you ask the Morse function to be non-degenerate, right?
Exactly.
That's
Exactly.
the thing.
Exactly.
Okay.
So, exactly. Exactly. Thank you. I've never thought it that way, but for me, it's just something that is really, it used to be something that it really works, and then you just blind-eyed, you just go ahead. But that's precisely the situation. Exactly. So basically, you don't want a critical point having an accumulation point. Something like that. All right. Here are two examples. So here is a nice simplicial complex, a little bit round, who cares? But it is a simplicial complex up to homotopy, up to homeomorphism. And I'm going to put heights, the heights that you would imagine. So this is at height 0, this is height 1, these two guys are at height 2, and this guy is at height 3. All right, so this is a circle. We know it is a circle. Its homotopy type is that of a circle, but it has too many cells. It just has too many cells. And I would like to simplify this whole thing. However, this function, like in there, is not Morse. For instance, here's a problem. Well, let's look at first at the non-problem. This cell, namely this cell, it's at height 2. And if you move to this phase, it goes down. That's okay. It's allowed. But if you move here, oh no, it goes to a higher level. So this is one of the exceptions for this guy. This should be an exception, right? Now, so far so good. But what about this? All right, this, look at the second one. You have to try also the cofaces. And it has this coface and this coface, and in both, it goes wrong in the incorrect direction. So this is not a Morse function. But let's do the same thing in this way. 3, 2, 2, 1, 1, and 0. So if I 3, 2, 2, 1, 0. Now this, you have to make this carefully and make sure that this is indeed a critical, sorry, this is a Morse function. So if you want to proceed like a computer, let's just do for every alpha. We have to check every alpha condition. For instance, for this cell, it only has two faces and both, it doesn't have any exception, right? If you go to the lower faces, it indeed goes to the lower dimensional faces, it indeed goes low. That's fine. This alpha satisfies the second condition. What about this guy? This guy, if you go to this face, it goes down. But if you go to this face, it goes wrong. So there is a problem with these two guys so far. Now, you cannot go up because these are top dimensional cells. There is no sense, there is no point of checking the first condition because there are no, this does not have any coface. So this is why I'm checking the faces, the cofaces. So we already had this, and this is the only exception. And we, by the same reason, for this cell, this is the only exception. Now I'm done with considering one-dimensional cells, and all of them satisfy this condition. Either the top one does not have any exception, or this one has at most one exception. Now, what about alpha zero-dimensional? Well, it might be this one, maybe this one, and maybe this one. Zero-dimensional cells have no faces. We have to go to the cofaces. And for instance, this one goes up. That's okay, because we go from dimension 0 to dimension 1, and it goes up. And this one is the exception, the one that I already noticed. So this is a pair of friends. And that's it. So this guy has this exception, just as this guy has this exception. Now, similarly, this one has the same thing, because this is quite symmetric. And this guy has no exception, because as you go up in dimension, you go in height, up in height, and the same here. So this is special. So let me just encode this information by saying that these two guys are paired. And I'm going to write it like this, saying that that's the exception for each one of them. But I'm going to be moving from the lower dimensional cell to the higher dimensional cell, from dimension 0 to dimension 1. This is what we want to understand, and let me just put it formally, but it's just combinatorial meaning. But the idea, of course, is, as I showed you in previous pictures, is that the idea is we want to push this guy through here and collapse this whole cell until we reach the other point. And the same thing here. We have to push this guy and collapse this cell until we get to the rest of the sides. In this case, there is only one opposite side. And this guy is just going to be stretched. And after doing that, we get the cellular structure of the circle given only by one zero-dimensional cell and one-dimensional cell. And that's optimal, certainly. So what we've done here is to say, well, this is redundant and this is collapsible. This is redundant, you don't really need it, and this is going to be collapsible. And the only thing that is critical, it has some topological meaning, are the two non-paired cells according to those exceptions. So, well, let's make some definitions, I think. So, the first proposition is that in this context, if F is Morse, then this is actually a lemma. Then both conditions can not fail. Namely, those two conditions that I wrote over there. For being Morse, you are entitled to have an exception up, and also you're entitled to have an exception down. The first thing to observe is that if indeed this happens for all alphas, then either you have an exception up and no exception down, or the other way around. So there's only one way, one role that is going to be playing. And the proof of this is actually very simple, at least schematically speaking. Namely, suppose that you have alpha, you have beta, and you have gamma. Pictorially, this is a two-dimensional cell, but it might be higher. Here is a one-dimensional cell, and here is zero-dimensional cell, but it's just only if they go down by one dimension, right? In general. Now, if it is an exception, it is because this higher cell, higher dimensional cell, is lower than this lower dimensional cell. So it means that you have this kind of thing, which points to the exception for not preserving the dimensions of the cells. If you go in dimension higher, you're expecting that the function is higher. But if not, then it's because if you go from this guy to a higher dimensional cell, function actually decreases, or at least stays the same. So in a sense, this indicates the direction of decreasing of the function in those terms. All right. Now, so suppose this guy, beta, satisfies that both of those sets have an exception. It also has an exception up and an exception down, which are, and suppose that the exception below is gamma, and this is why, because this lower dimensional cell is actually higher than this higher dimensional cell. And also this guy has this exception, which means that if you go from this lower dimensional cell to this higher dimensional cell, function really decreases. So that's what you're picturing there. But now I'm gonna use the condition that this complex is regular. If it is regular, part of this direction, there must be another. So what we have here is gamma, phase of beta, and a base of alpha. I want to convince you, at least geometrically or in the picture, that there should be another phase in between them. This is quite obvious in the simplicial case. You just have a tetrahedron. There's plenty of phases there. But in general, if the complex is regular, what it happens is that there must be, this guy cannot be the only phase of this. Because otherwise, if this is the only phase of this guy, then it is mapping the boundary of this, which is a sphere of some dimension, is mapping onto this single thing. But this is contractible because it's a cell. It cannot be a homeomorphism because the thing had attaching maps which were homeomorphisms. So cannot be anything. It cannot be that beta is like the other thing. So essentially, you just take anything. This has to lie in another cell, in another. It has to be a phase of another thing, which is a phase in turn of this guy. So essentially, the fact that it is regular, as I said, in the simplicial situation, this is very transparent. Otherwise, you have to do a little bit of topology or just make a sort of thing like that. It means that there is another phase of alpha having gamma as a phase. But then this guy already has this exception. So this guy cannot have this as another exception because of the second line there. It goes up in dimension, but this is the only one that went down. So this must be in this direction. Namely, this cell is indeed beta, is higher than this cell. And the same here. Alpha already had this exception. Going from 2 to 1, but they hide the other way. But so this beta, which is also a phase of alpha, cannot be an exception, which means that it goes like that. So look at here, I have this cycle, and it says that the height of alpha is higher than this, higher than this, higher than this, and higher than that. Contradiction, because at least two of them are strict, namely the ones that are not exception. So only one of those guys fails, if any. And then this entitles you to do a classification. If you have such a Morse function, then you can classify the cells in the phase pose set. Namely, you can say there are three types of cells, namely the collapsible, redundant, and the ones that have no friend. It reminds me of my childhood. So these are the guys that for which fails the first condition. It has a phase, lower dimensional, which actually is up higher. And any one of these, it would have a friend here for which that guy original is also the exception of that, naturally. And the other way around, any redundant cell is because it has an exception of a higher dimensional cell, but which is lower. And this guy must have also this guy as its exception, but it's unique because there is almost one of them, and can be done. So this is unique. So this allows us to make a pairing, call it matching, between these kind of cells and these kind of cells. And of course, this is the union. Let's call this C, the set of collapsible cells. Let's call R, the set of redundant cells. And sorry about that, didn't see it, criticals for the set of critical cells. Then we have a one-to-one bijection between C and the collapsible. And here is bijection. It's not because it's bijection, it's a vector field. And then you have the critical ones. Right? So that's the definition of having a discrete vector field, but it captures the image that is in there. Essentially, it wants to, because of Adolfo said, it's kind of modeling what happens in good behaved, more smooth Morse functions. So you have essentially that, and this is what is called, then under these conditions, this is called a gradient vector field determined by the function on X. Very good. All right. So what can I do with that? Now, once you have this perfect partial matching, it would be a complete perfect matching if it matches all the cells on X. But it wouldn't only if it has an even number of faces. But in general, I might leave out some criticals. Once I do that, I can talk about the B modified gradient field determined acid diagram determined by D. What is that? So think of the Hasse diagram of X. Here you have your list of cells, and any two consecutive lines differ only by a dimension, by one. And then you have, well, this guy may have these two faces, and then this guy may have these three faces, and this guy may have four faces, and whatever. Now, this perfect matching is associating some special faces which are exceptions. And what I'm going to be doing, recall that the Hasse diagram by convention was constructed with all arrows pointing down. Now I'm going to reverse those directions of the in the original Hasse diagram whenever these two guys are a pair of exceptions for this sort. So you're just reversing a few of the arrows in this huge Hasse diagram. Now you have the original one does not have cycles because all of them go down. It's impossible to have a cycle. But now sometimes you go up once you've done this thing. And the thing to realize is that if you do that, the new graph, directed graph that you construct, does not have cycles. The proposition, the Hasse diagram of X modified by B, by this vector field, coming from some Morse function, is acyclic. This is not homology, sorry. This is the Hasse diagram that I just described, is acyclic. looks wrong. It might be wrong. Is it basically? You know, that's fine. So, well, and that's quite easy because look, when constructing the Hasse diagram, we only change the directions of things that go actually lower. Even though the faces which they are paired are higher dimensional, actually the height is the opposite. Those are the exceptions. So there cannot be, simply it's quite obvious there cannot be any in the modified stuff, there cannot be any cycle because a cycle must, originally everything went down. So if you want to have a cycle, it has to involve something that goes up. And then, well, you would have, it would have been involved in some cycle. But in this cycle, since you have to go down, say you started in here, and then you go up. Eventually, you have to go down because you have to be in this dimension, not in this dimension. Once you go down in the modified diagram, the function actually is strictly less. Those are not exceptions. So it cannot be possible that if the height stays the same or goes lower, and eventually it really goes lower, remains with the same, comes back to the same value. So this Hasse diagram is indeed acyclic. I don't know if I explain myself. Is it clear? The point is that in the Hasse diagram, this is pointing for cells that is higher dimensional, lower dimensional. But whenever I'm going to invert a reverse of an arrow, that means that this is this way. Whereas the ones that do not increase is because they are this way. They are not exceptions. So these are okay, but once you have one of these, this really goes low. And if you only follow these kind of arrows, it would always be descending, 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 but it has to involve one of them because otherwise it would not come back to the same original point. So it cannot be possible. Not only that, well, that gives you. All right, so here's an example. Let's be a little bit more precise. So recall the Hasse diagram that I talk about of a triangle in which everything goes down. And now here's an example. For instance, suppose I reverse these guys. Notice that I could not reverse these guys because then I would have red ones go up, are the ones that are inverted. Yellow ones go down, are the original ones. And if I also reverse this guy, I would have a cycle. This is not allowed. But so far there are no cycles, and it's quite easy. You have to make sure that it doesn't have any cycle. You have to start either here, here, or here, but obviously they cannot have here. So you only have to scan all possible ways of going from this into blah, blah. But the only thing really relevant is like that. It's not a cycle. So this is an example of a gradient field defined on this. Now, what's the difference? Notice that I define a gradient field, namely this partial perfect matching, out of a height function for the body centers of the faces of a simplicial complex, say. What's the difference? If I have something of that form, such a thing, does it have to come from some Morse function? One of these having this weird property of having a limited number of counterexamples. And the answer is yes. There is a one-to-one correspondence, basically, between Morse functions and this kind of discrete gradient fields, which are acyclic. Well, I already said the word gradient. By definition, a vector field is gradient when, namely a partial perfect matching, when it has no cycles. For instance, the one defined by a Morse function is gradient. But it's basically that, a theorem. So we have here the set of Morse functions on X, satisfying those two conditions. And then I have here the set of gradient vector fields on f of x. And I already defined a way of going from the left set to the right set. The point is that this is surjective. Let's put it like that. Every gradient field, every gradient vector field, it comes actually from a Morse function. And the proof of this is quite, it might be a little bit technical, but it's really, I learned this from one of the participants here, Tere, which it uses only graph theory. Essentially, in a directed graph, there is always a function that goes down. And if it is finite, if it is not finite, things, I'm not sure about that. It might be, I'm not an expert in Morse theory, in graph theory, but in finite things, which are using here, and I'm very accepted about the acceptic about the non-finite case, because for non-compact manifold, things can get a little bit weird when you don't have lines that really start somewhere and end somewhere. So it's the thing is a little bit different. But if it is compact, namely finite, our simplicial complex, then that's okay. And you can actually show that anything like that comes from such a Morse function, one satisfying those two conditions. And it turns out that this is all you really need to deform things. You only need to understand where to move, as long as it is a unique way of moving. And the ones that of deforming, of pushing, collapsing, and the ones that are not deformed or not stretched are just, well, the ones that are not collapsed are just stretching and filling up spaces of other cells until you get a simplified cellular structure, as in the examples in the previous session. So essentially, it tells you that this is the same thing up to an equivalence, namely the equivalence determined by this function. And it means that if you have two functions, it might have, which might have different values on different cells, but the way that they compare the exceptions is the same, for me, is just good enough. So they define the same gradient field. All right. So here's the proof. I don't think I'm going to have time for that. So let's move on to a, let's move on to an explicit algorithm. Well, the thing is that either you have to construct a function, a Morse function, on a given simplicial complex, or maybe it's simpler just to make relative comparisons, not actual values of the heights, and produce a graded field.
So basically, a gradient vector field is just reversing arrows from the Hasse diagram and just making sure that you don't create any cycles, or you remove all the possible cycles. Well, there is no cycle because it's lower down.
There are no cycles, so you better keep that condition.
Okay, is that it? Right, that's the definition.
That's it.
Okay, no, I just want to clarify that. Thank you.
That's it. This is the same definition that you mentioned here is this, together with the observation that there cannot be equality in both sides for some given. All right. So, but then you want to use this to analyze some data set. You want to use this technique. I'm going to tell you how to compute homology. I'm going to tell you how to compute fundamental groups in terms of such a thing. And this is quite interesting because then, well, this has been done apparently in the last 5 years. Some people have used maybe Pavel, the persistent homotopy groups, so at least fundamental groups. And it's a matter, you could say, let's just do persisting whatever for any kind of a technique that you have in algebraic topology, which is homotopy invariant, and then you can extract information out of geometric objects. The problem is that many of these tools are difficult to compute, or not algorithmic, at least yet. So, but in the case of the fundamental group, there is indeed a way of computing them. If you have a simplicial complex with one of these gadgets, then you can easily compute, or with the help of a computer, the fundamental. And then you can do persistent things. Well, I should say, but I'm not an expert on that. Just as you define gradient fields on a single complex, well, this might not be a complex. It may be a filtered complex. And then there is a way, as far as I understand, to defining vector fields which are filtered, which are compatible with this filtration of the complexes that you were starting to talk about. Because then you want things to be kind of functorial and easy to compute. You can, if that happens, then you can compute homology more or less easily. However, I should say that that's not really necessary. You can compute these kind of things, the fundamental group or the homology or whatever, between X and Y. And for any map, which is, yes, cellular, it has to send cells into cells, at least cellular in this strong way. But it doesn't have to send critical stuff into critical stuff, or collapsible stuff into collapsible stuff. No, not at all. But still you have then, if you want to use these two gadgets to compute correspondingly these two guys, you have to do a little bit of more work to actually say explicitly what this induced map is. So in my view, although I'm not an expert, as I tell, in order to avoid this extra computation is that you impose, if it is an inclusion, then you want the discrete vector field is, the gradient here is here compatible with this over one, and then it's more or less easy to compute, at least with a simple way of, and with an algorithm. All right, so I'm gonna make a detour in the last part to, so this course is telling you how to compute fundamental groups with this thing, telling you how to compute homology, telling you, therefore, how to compute cohomology, and telling you also how to compute additional stuff. For instance, cohomology, if you've reviewed these things, comes with more natural, additional and natural structure than homology. Cohomology forms what is called, especially with coefficients in a ring, is called a graded ring. You have cup products. You have additional structure that gives you more information on the geometry of the space or the information that you are measuring. But there's a lot of things, not only cup products. You have steroid powers, you have higher order operations like massive products, or actually some other kind of operations, which are really very difficult to compute. But if these things can be defined at the level of complexes, then you can just do this technique to actually compute them, not because of big theorems, or just put the computer to work to compute it for you. All right, so what I'm going to be describing is a precise algorithm to produce a gradient field on a given X, let me just call it K, simplicial complex. Now, I already mentioned in the previous session that there are several algorithms. For instance, there's a Brazilian guy, Lewiner, that I know that he worked not long ago, maybe 10 years ago, maybe a little bit more, in dimension one. There are efficient algorithms for computing gradient fields of graphs, say. That's more or less understandable, it's believable. And I think he also describes some things in dimension two. And he wanted to apply them to analyze images and many actual applied topology. Now, as far as I understand, there is if you want to compute homology of some complex, or perhaps a filtered version of that, There are indeed, well, there is a way of doing that. Homology is, you know, or you will know, it is a computable stuff. It's you can just use Gauss reduction to compute homology. However, this is a very expensive, tends to be an expensive procedure if there are a lot of cells, a lot of sequences. So you really want to improve things in order to produce a package software that computes these kind of things, or in the filtered version. And one of them is Perseus, if I understand correctly, which is based precisely in producing discrete vector fields first in order to simplify the computation of homology, because you can produce a discrete vector field with very few critical cells, and then the computation all of a sudden decreases. And that, even though you have to produce your field, it's much faster than just trying to do Gauss reduction from the beginning. Now, and I already said a few words about this procedure. It's basically based on the fact that if you have free faces, just push them, have no problem. And whenever you are run out of free faces, just remove one of the cells, you declare it to be critical, and just keep on doing that. Essentially, that guarantees that you will be having no cycles. You're removing the way in which there will be a cycle. And I believe that Vidit Nanda, which is the guy that I think put that software to work, is based on that reduction-co-reduction method. But this is an alternative procedure, which you can prove, we proved, that has the same complexity, computational complexity. It's just as expensive as the other one. But at the end, I'm going to be telling you why it might be a little bit better than, than the other one. Or maybe a mixture of them could speed up computations. All right, so now, this algorithm is not mine, not at all. It is of a student, a PhD student. It's just about to finish, by the way, Emilio González. Somehow, I don't know, he is a bright guy and devised this procedure. So this is due basically to him. And it goes as follows. So suppose you have a simplest, which is a simplicial complex, which is order. So I'm going to be working essentially in the category of order simplicial complex. What's that? Well, you have a vertex set. So you have family or subsets of some given set of vertices. So let's call B this set of vertices. And I want to put an order, at least a partial order, on the set of vertices. Now, you can always order it if you want to linearly, but it has to have the property that restricted to each phase is linear. It is linear, it is total order on the faces. But maybe there are some vertices cannot be compared. Anyway, there is a order principle, order extension principle that tells you that essentially any such thing can be extended to a linear order. So it's not a problem, say that this is linear. Put a linear order on the vertices of the simplicial complex. And you can think of it is actually vertices are vertices, just so objects. You say vertices go from 1 to up to n. You've numbered them and you call them by these numbers. All right. Now, what is this algorithm? Okay, this algorithm goes like that. There's going to be, it's an algorithm that consists of a union of processes. So let me tell you a little bit more. What I'm thinking here is the Hasse diagram of K. Think of the Hasse diagram. And this process is going to start trying to make, like crazy, pairings in the top dimension, let me call it D. D is going to be the top dimension, the dimension of K, trying to do pairings in this way. 1, 0. By the way, in order to motivate this, let me give you first an example. So suppose you have a tetrahedron, 1, 2, 3, 4. And then you have the phase 1, 2, 4, and so on, and etc. Edges, vertices, and so on. Now, there is a well understood, this is contractible, and actually you can say, well, you don't have to do much, but for instance, you can just contract everything from top to bottom to this form. But then let me do it in this kind of organized collapse way by a field. Well, you can do this process of inclusion, exclusion with respect to some vertex, say the larger one. What is this? What I'm going to do is take a simplex here, and I'm going to tell you which one is your partner, is the partner. Either if it has a partner there, or if it has a partner there. But it has to be only one. It has to be a perfect matching. All right. Well, the only thing is that you can do is, well, if 4 is not in sigma, then sigma is going to be paired to sigma union 4. It didn't have it, but put it in there. This is supposed to be a solid tetrahedron, so all the simplexes that you see them, there are. For instance, if you have sigma is 1, 2, 3, then you pair it with the whole simplex, the whole tetrahedron. Now, if sigma does contain 4, remove it, exclude it. So sigma is going to be paired with sigma minus 4. This is a standard. What you're doing here, for instance, say, what do you do to this zero-dimensional stuff? You pair it 1 to 1, 4, because you are putting it in there. 2 to 2, 4, and so on. So what you're doing at the level in between cells of dimension 0 and dimension 1 is just pushing them up. And for instance, this guy, 1, 2, 1, 2, it doesn't have 4, so it has to be paired 2 with this guy. So this is pairing this with this face. And so on. This one is pairing this, and on the back, 1, 3 is being paired to 1, 3, 4. We put it in there. And finally, 1, 2, 3 does not have 4 and has to be paired to 1, to the whole tetrahedron. It is quite transparent in this picture because there are no identifications and everything goes up, that this cannot have cycles. So here is a gradient flow. And essentially, this is the one that you were expecting. Everything is being pushed all at one time. For instance, this two-dimensional cell is pushed from the bottom to squeeze everything to this inverted cone. And once you do that, then you have this two-dimensional cell, you squeeze it, squeeze it, squeeze it, and then the 3 lines, and at the end you get one single point. Well, Emilio's algorithm is a very natural generalization of this inclusion-exclusion principle, except that here, everything, every subset of 1, 2, 3, 4 is in there, and this has no problems of being defined. But if you have a more general simplicial complex, then not every subset of the vertices will be a simplex. Only certain ones, the ones that belong to the simplicial complex. So what you do is, well, what is PI? So this is going to be an algorithm consisting of a sequence of subprocesses, PI, going from this dimension to this dimension. The idea is that I want to make this kind of pairings. When I'm done, I'm going to be these pairings. When I'm done, so on, until I do all these possible pairings. So what is P to the I for one of those I's? Well, this consists of a union of the sequence of P, I, V. where V lies in the vertices, but goes from the top one to the lower one. Recall that the vertices go from 1 to n. So you start, this is the role of the 4. This is the B, this is like the B. I'm gonna try to include or exclude with respect to some B, but now I have to try them all. All right, so you do this. And I haven't defined this, but if I did, I have defined this. So what is PIV? PIV, all right, do the inclusion-exclusion principle with respect to B for in this, between, well, it would be in between I plus 1 and dimension I. So suppose you already started this algorithm, well-defined, and you already have made some pairings. You keep a list of your pairings. And if your two cells are already paired, you remove them from the set of available faces at that time. Then once you get to that and you start to running this guy, what you do is, okay, see which of these faces are available, have not been paired, which one of these have been are available, and then just try to put V to this one if it exists. Namely, here's a face. You say, okay, B does not belong to there, all right. And if I put it, is one of the cells that is still available, yes or no? If it is yes, that's a pair. You immediately do it and remove it from the available cell. And just keep on doing that. Namely, you look for these guys that admit a partner here in the inclusion-exclusion principle with respect to the B, the current. And that's it. And that's it. That produces a list of pairings, a list of friends, which you can prove. It's a little bit technical, but it's not so very complicated. But this is really, you have to do things carefully, which is acyclic. So this algorithm produces an acyclic field, gradient field. All right, so now part of this course is telling you that this is a very efficient way of producing vector fields. And let me just work out a few examples so to show you that that's indeed the case. We have tried in surfaces, we have tried in obvious things that a topologist would care about, and not always, it is not always optimal. I have to say what it is optimal. But it depends on the numbering. You can have two vertices and say, this is not the first one, this is not the second one, maybe change the ordering. It depends on the order, the original order, but almost always with the most natural order, you produce a pairing B, which is maximal with this algorithm A. What does it mean to be maximal? It means that not only it is a vector field, a gradient vector field, it is acyclic, but if you have one of the critical cells, which hasn't been paired with anyone, nor on a coface or a face, then all of its faces and all of its cofaces are already being paired. Either this guy is here or these guys go like that. It is really isolated. Because if it was not isolated and one of these gammas was a face of this guy, at certain moment of the algorithm, you would have to be asked, what is the vector, what is the vertice here that does not lie in here? And at some moment, you would have to be at that point, and then you would be asking this question, and this would have to be paired. So this, in this sense, this is maximal. There is no room for adding one additional pair to this gradient field. So this is very good. That doesn't imply that it is optimal, but it usually is optimal. What is it? What does it mean to be optimal? Well, you could say in each dimension, the number of cells is precisely the Betti number of the homology. That would be a good situation, and that is not really necessarily the case. Another way of saying that is that if you have a vector field, which is gradient, it would be optimal if the Morse complex associated to X, namely the space, the cellular complex to which X deforms into, that I described in the previous session, has a chain complex whose boundary is trivial. If that is so, then that would be the homology of X, of course, and then it would tell you that the number of cells in each dimension is precisely the Betti number, and you cannot do anything with lower. So this algorithm that I just described is maximal, might not be optimal, but it's in general, close to being optimal. All right, so let me just work out an example very quickly. I'm going to be using this example later for some of the problems that I'm going to assign you. And so suppose I was planning, as I tell you, but I didn't measure quite well the time. I was planning to work out the Duns cup here to answer this question of Jesus, that I was curious about whether there is a vector field, a radial vector field, which has only 0 and 1-dimensional cells, but get rid of the set of 2-dimensional cells. It is known, as I told you, that this space is contractible, but it is not nicely contractible. So in general, it would not be possible to get one single 0-dimensional critical cell. But in your original question is, can you actually lower it down to, say, 1? All right, so, but I haven't worked that example, so I'm going to tell you about the example that I do have worked out, because otherwise might run into trouble. I'm an expert on that, and the Blackboard, just getting into problems myself. And so what is a projective plane? Projective plane is the sphere divided by antipodal points, right? And here is a model of the sphere. Here is the, well, it is the same thing as a disk divided by antipodal points in the boundary, just the top. And you only identify these two things, because if you are going to identify everything, the low part is going to be identified with the upper part. And you don't really need a disk or square or whatever. I could use this triangle and make these kind of identifications. This is going to be identified with that. This is going to be identified with that, and so on. But I want to triangulate this. And well, to make it, not to run into the problem of having a true, honest triangulation, well, you have to actually subdivide to make apart the identifications. And one way to identify things to make that work is like that. So I have here 1, 2, 3. This is 3. This is 2. This is 1. And for instance, of course, this suggests that 1, 3 is identified, this line is identified with this line. 3 to 2 is identified with this line. And 2 to 1 is identified with that line. And of course, what you're doing at the end is identifying antipodal points on the boundary. This is the projective plane. All right. So let's just, I want to go through this to make sure that we understand the easy definition of the field, of the algorithm. So there are the Hasse diagram has only 0, 1, and 2 dimensions, 3 dimensions. And I'm going to be pairing between these two guys. So now I did this very carefully and not going to, hopefully not do any mistakes. So let's see. I start being 1, start trying to do these kind of things. And then the vertex then I have 4, 5, and 6. So the vertex starts being 6. So I want to do the inclusion-exclusion principle with respect to 6, with whatever is left at the beginning, everything. So now I need to use another color, yellow one. Do you see this one? All right. So here's one pairing, because this edge does not have 6. But in order not to get into trouble, 2, 3 has already been paired like that. That will show that so I have this, which goes like that, and I have this, and I have this, and I have this, and that's precisely, I have run P1, 6. I have done this inclusion-exclusion principle with respect to, in between 1 and 2, with respect to 6. And I have to remove the cells that are already taken, like this edge, like this triangle. But of course, I'm not going to be erasing because it's going to be a mess. Only I'm going to see that the ones that are already taken, either as the tail or as the head of the arrow, you cannot play with them. They are no longer exist. Now, let's play with 5. With 5, let's see. What you have to do essentially is look at 5, look at the link, basically, and only the faces that are opposite in the link to this guy. And then you would like to do this guy, but this is already been taken. That does not exist. Now you do this. You would like to do, let me just write this correctly. You would like to do this, but this guy does not exist. This is not possible. And one does this, which is already there. And this is not done because this was already paired against 6. And I've done 5. Let's do 4. 4. I cannot, let's look at the link. So I cannot do this because this edge has already been paired. I cannot do this because this edge has already been paired. Cannot do this, or this, nor this. So 4 does not create any additional stuff. Let's see, 3. 3, here's the link, this and this. Okay, this one you can do it. Oh, well, I don't have it. Let's see. Against 3, this is not being used. So I have this guy. This is not possible. This is possible. And then I would like to do this, because the link of 3 is this part. So I would like to pair it like that, but that's already been taken. And I would like to pair it like that, but that's already been taken. So 3, it's already done, only creates this one. And now do 2, 2. You have here 2, 2, and this is the link, and also this one. Then I would like to push this in this side, but notice that this line, which is want to go in this, has already been taken in this direction. This is not possible because this is already been taken. This is not possible. This is not possible because this has been taken, and this is not possible. So this does not create anything. And then 1, let's see, 1, you cannot, in this link, in this part of the link, nothing can be done because these 3 things do not exist. And this has been taken. And the only thing that you could do is this one, but these guys have already been taken. So that finishes up to this point. And now I have to do the same thing with I equals 0 to do the additional thing. That's going to be very easy. But let me make one single observation at this point. Notice that all the cells have been paired. Of all 2-dimensional cells have been paired except for 1. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 cells. And this one remained critical with no friend. All the others either, well, they must be heads of arrows. They cannot be tails because there is nothing in dimension 3. So it already gives you a critical 2-cell, and an optimal decomposition of the projective plane involves necessarily a 2-cell. So far so good. We are close to optimal actually. Now let's do this case with B equals 6. Well, now I'm pairing vertices, cells of dimension 0, to edges just by trying to include number 6 or 5 and so on. Well, everything happens. This guy is paired like that, and I better remember that. This guy is paired like that. That's it. That, and like that. 2, it's being paired. 3, it's being paired. And all of a sudden, the algorithm would have to go all the way down, but you can just say, well, you have to stop when you cannot do anything else. At that moment, you notice that there is one single critical, well, all the vertices, 1 has been taken. 2, like this. 3, like this. 4, like this. 5, like this. And 6 is the only guy that is critical. And in the rest of the algorithm, I'm going to be trying to put 5, 4, 3, but it would not be possible. Essentially, this is the only one that is critical. If this is going to be paired with someone, it would leave no critical cells, dimension 0. That's impossible in a gradient field. So essentially, this is it. And now look at the critical cells like that. Let's see. Look at this cell. This is critical. All other edges, you can check one by one, taking into account the identifications that are already being paired. And 6 is critical. And that leaves for us this optimal gradient field on the projective plane, having one single cell for dimension 0, 1 in dimension 1, and 1 in dimension 2. Cannot be anything lower because of the homology mod 2 of the projecting plane, for instance. So to finish, let me assign you this exercise. The next talks, I'm going to be describing how to use these kind of things to compute invariants, homotopy invariants, like fundamental group in homology. But for the moment, so I want you to run this algorithm to compute a gradient field using the theorem that you do have something that is acyclic on this triangulation, say of the torus or the projective plane, depending on the application that you do. Do it. I already done. It's already maximal for certain numberings. And most likely it would be the one that you choose. Yes, the Klein-Bottle. Either the torus or the Klein-Bottle. And another assignment, if you've already done that, or if you want to do complete the assignment of Jesús, just take the Duns cap, namely like that. I was remember how is it obtained, and produce, and you have to produce a simplicial structure, and then run this algorithm. And I would be curious to know if you can get rid of the 2 cells. You cannot rid of the 1 cells, 2 and 1 cells, because then you would have that the Duns cap would have the homotopy type. Well, would have by simplicial collapses the homotopy type of a point, but that's not to be the case. But I would like to make sure that you can actually get rid of the 2-dimensional cells. And once we work those examples, we will have with the next things that I'm going to be telling you about, something to put on our hands on and compute homology. In the meantime, and homotopy groups. In the meantime, for those that know how to do implementations, I want you to implement this algorithm. It's not difficult. I've already done it in Mathematica, which is the only system that I know because it's really very friendly, but it's not the most convenient thing if you want to do actual implementations, fast implementations. So I would be interested if you to see if you can do one of these implementations in a sophisticated way, so it is fast, and then make something that compare it with the best implementations for computing homology or persistent homology. All right, let's
thank Jesús. Are there any questions?
Thanks. This algorithm is not optimal, but for example, in manifolds or something like that, is optimal? No? Okay. Because it's very good. It's a very nice algorithm. No?
Produces very nice. At the end, I was planning to tell you some things. Look, there are some this kind of configuration spaces for complexes. This has to do with this is a subcomplex of x to the n, and these are pairs. These are n tuples, so that xi is different from xj for I different than j. Yeah. And this is the space of states of some system of robots that move in X without collisions. And well, in any case, these kind of spaces are typical and are ubiquitous in algebraic topology and other areas. So my original interest came from this kind of spaces. And it turns out that these spaces, at least when Gx is a graph, you can define a discrete model of it. Originally this is a space. It's actually an open manifold. If this is a manifold, for instance, but you want to make it discrete. And in the PhD thesis of Aaron Abrams, he introduced a way of producing a different space. So here you have a discrete version of these spaces, which sit inside there. And one natural question is whether this is a homotopy equivalence. And if G is a graph, it's more or less easy. It's more or less simple, relatively simple, to guarantee, depending on, you have to subdivide possibly G to get a homotopy equivalent. So this gives you a way to understand these kind of things. And then we use this, at least in the case of two things, in order to understand the topology. Tere's thesis has to do with that, if I remember correctly. Emilio's thesis also, but mainly, now, what happens if you put another complex, say a simplex? These are classical. This one is just as if you had put, another dimension. Euclidean space. Configuration spaces on endpoints on Euclidean space, typical thing. They are well understood. Homology, structure of coproducts. They have a minimal model for the cellular structure. Very, very nice. But now let me try to think of this, but say, not taking the whole simplex, but a some dimensional skeleton. And my answer is that in that case, using this algorithm, you can actually give optimal indeed. What you get is not only maximal, but indeed optimal things that not only tell you what the homology is, it tells you what the homotopy type of this is. Because you're lucky enough to see that there is only one single zero-dimensional cell. There's a bunch of cells of dimension and fixed dimension that forces on the nose a wedge. And then there is one extra, sometimes there is one extra cell, and one can actually show that it is, the attachment map is trivial. So in many cases you get optimal things, and not only optimal in that sense for homology, you can get at the homotopy type.
Thank you. It's very interesting.